Chapter 28, Review. Number 1. You are drawing 100 times at random with replacement from a box. Fill in the blanks using the options below. So the options are 1 sample z-test, 2 sample z-test, chi-squared test for the contents of the box, and the chi-squared test for independence. So A, to test the null hypothesis that the average of the box is 2, you would use so if I told you the box has an average of 2, what would you do to test that? You would do 1 sample. Okay? So it can't be number 2. Now, is this going to be a z-test or a chi-squared test? Z-test. How come? There's only 1 sample and there's only 1 category, the average. So it would be a 1 sample z-test. Number 2, to test the null hypothesis of the box, that the box is 1, 2, 3, you would use, so would we use a 1 sample z-test? No, why not? There are 3 categories and we want to test all 3 categories. So it's not a 1 sample z-test. Is it a 2 sample z-test? No, for the same reason. So now it's a chi-squared test. Is it a chi-squared test for the contents of the box or a chi-squared test for independence? It's 3. Chi-squared test for the box. What is a chi-squared test for independence? If it's to test whether 2 things are dependent or independent. So if you were testing, let's say, gender and ice cream preference, then you only do 1 sample and you ask everybody 2 questions. What's your favorite ice cream and what's your gender? And then you can do a test to see, does gender influence ice cream decision making? Can you test whether ice cream decision making affects gender? No, because I don't know. Maybe I shouldn't go into that. Let's stop now. We're entering a politically charged area, so we're done. Number 2, as part of a study, I really need to learn how to edit videos. As part of a study of the selection of grand juries in Alameda County, the education level of grand jurors was compared with the county distribution. So we did one of these that dealt with age, and we decided that age had a huge effect on whether or not people were chosen for jury duty. Okay, so we have, as far as education level goes, 28.4% of the county had an elementary education, 48.5% had a secondary education, 11.9% some college, and 11.2% had a college degree. And the actual number of jurors chosen were 1, 10, 16, and 35. So we want to see, are those numbers, the actual numbers, representative of the actual composition of the county? Okay, so how are we going to do that? Well, first off, what is this? Is this an observed value or an expected value? Observed. How come? That's what happened when we hired juries. You make a lot of money. You make like $5 a day. It's great. I don't know. It might be more than that, but it's not very. Yeah, it's great. All right, so what we need to do is build a second list of expected values. How are we going to do that? We need to take these percentages and multiply them by the total number of jurors. So 0.284 times 62 gives me 18 jurors. So if the selection process is independent, or sorry, that's not right. This is not a test of independence. Well, no, I guess it is. So if the selection process is fair and it puts each group in separately, meaning independents, then 28.4% of the jurors should have an elementary education. And it turns out only one of them did. So for the next one, secondary education, which would be high school, 0.485 times 62, and I get 30. And 0.119 times 62, and I get 7. And then 0.112 times 62, and I get 7.44. Okay. Oh, why did I do that? So now the question is, when I add those up, do I get the right number? 14, yeah we do, 62. It worked out. Sometimes it'll be a little low because we rounded down a whole bunch of times, but in this case it didn't end up mattering. All right, let me get my hand calculator because I'm faster with it. Now what do we do? Calculate a chi-squared test. So we always do observed value minus expected value squared over expected value. So 1 minus 18 squared over 18. So I'll type that in. And then we add that to, can't really see this, 10 minus 30 squared over 30. Plus 16 minus 7 squared over 7 plus 35 minus 7 squared over 7. And I get a chi-squared value of 169. Okay. How many degrees of freedom are there? Well, we get rid of one row, one column, and one row, and I end up with 3. So now in the book, I have to go back to 527. And I have a chi-squared table, 3 degrees of freedom. Where is my chi-squared term of 169? It is so far out to the right, it's absolutely ridiculous. So, are these jury members representative? No, they do not represent the education level. Does that mean they're not a jury of our peers? That is up for debate, because the Constitution does not define peers. That's for the courts to decide, and I'm not sure what the courts have said. I'm sure they've said something, but I don't know what it is. Every time I've gone to court, I felt that it was a jury of my peers, so I didn't complain. In mathematics, we call that being vacuously true. So if something is vacuously true, it's true because there's nothing in it. It's a vacuum. So every time I've gone to court, the judge has had blue hair. Prove me wrong. And there is no proof that proves me wrong, therefore it's true, but it's vacuously true. Meaning it's only true because there are no examples to prove me wrong, because it's never happened. So I could say, all people who are 10 feet tall have 6 toes. It's true. Because you can't prove me wrong. There is no way to prove me wrong, because there are no 10 foot tall people. Okay. Number 2. No. Number 3. Oh, wow. There are a whole bunch of questions I didn't answer. Could a simple random sample of 62 people show a distribution level so different from the county-wide one? One, this is absolutely impossible. This is possible, but fantastically unlikely. This is possible, but unlikely, quite possible, or nearly certain. Is it absolutely impossible? No. Is there a way that we could randomly select people and end up with a jury that is so misrepresentative of the whole? It could happen, but it's fantastically unlikely. Right? It's like 0.0000000. I mean, it's so small. We can't even fathom it happening. It's probably a little less likely than winning the lottery. Right? Winning the lottery is so fantastically impossible or unlikely that it's not worth it. I had a stats teacher at CEU who would end most lessons with saying, and don't forget, the lottery is a tax on stupid people. So if you want to pay more taxes, play the lottery. All right, number 3. You do that. Good luck. Each respondent in the current population survey of March 2005 was classified as employed, unemployed, or outside the labor force. The results for men in California age 35 to 44 can be cross-tabulated by marital status as follows. So here is our table. That's not it. And then, oh shoot, I pushed the wrong button. So this is employed. The next one is unemployed. And then these are outside the labor force, meaning they're stay-at-home parents. They are 30-year-olds living in the parents' basement. They are people who are retired. They are disabled people who can't work. Maybe they are in jail. Yeah. Okay. So those people that are not actively looking for a job. So to be called unemployed, you have to be looking for a job and you don't have one. Otherwise, you're just considered outside the labor force, meaning they don't count you. All right. Men of different marital status seem to have different distribution of labor force status. Or is this just chance variation? How are we going to figure this out? So we have to use a chi-squared test because we have lots of categories. Are we going to do a test of independence or a test to see what is in the box? Test of independence. Okay, we're not trying to figure out what the actual numbers are. We're just going to use the numbers we have from the sample to see if things are dependent or independent. All right, I'm going to move this over just a little bit. So in order to do that, I need the totals. So 790 plus 98 plus 209 is 1097. And then 56 plus 11 plus 27 is 94. And 21 and 7 is 28. And 13 is 41. And then plus 56 plus 21, we get 867. And 116. 249. And then just to check, I'm going to calculate that total from both directions to make sure that I didn't make any mistakes. And I get 1230 one way. And then, is that 1097 or 47? 1097 plus 94 plus 41. Oops. All right, where's my mistake? So 209, 27, 13, 247. Oh, 249. Sorry, this is a 9. And then, oops. So this is 1232. Okay. So I need to go in and put numbers next to each category that are expected given the particular makeup of this survey. So 1,232 people participated, and 1,097 of them are employed. So what percentage is that? I'm going to take 1097 and divide it by 1232, and I get 89%. So 89% of the married people should be employed if this is independent. So I'm going to take 867 and times it by 0.89, and I get 772, which is not too far off. Now, 89% of these people should be employed. So I take 116 times it by 0.89, and I get 103. Okay, and 89% of these people should be employed. So 209 times 0.89, and I get 186. Oh no, sorry, 249. Thank you. So I take this number and divide it by this number, I get my percentage, and then that gets multiplied by each of the column totals. So this one is actually 222. So you guys got 222. Okay. Come on in. Come on in. Uh-oh, I lost my mic. There it is. Now we need to calculate the totals for unemployed for each of those three categories. So 97 people reported being unemployed. So 97 divided by, is that a 4? 94 divided by 1232 is 7.63%. So that means that 7.63% of the married people should have reported being unemployed. So we're going to take this 867 times 0.0763, and I get 66. And then I do the same thing with 116, and I get 9. And I do the same thing with 249, and I get 19. Okay. Now, 41 people reported being out of the workforce. So 41 divided by 1232 is 0.3327. Okay. So we're going to times that by 867, and I get 29 people. And then I multiply it by 116, and I get 4 people. And then I multiply it by 249, and I get 8 people. Okay. So now I have all of my expected values, what should happen if these categories are independent, and then I also have what did happen when I took the survey. So to figure this out, I just need to go through and subtract them and divide them and then square them and then divide them and add them all together. So the pattern is it's going to be 790 minus 772 squared over 772. And I'm going to do that with every single category. So it's always observed minus expected divided by expected. All right, so it's going to take me a minute to plug all this in, so I'm going to pause the video. Welcome back. Now that I've typed it all in and I push enter, I get a chi-squared term of 14.3. How many degrees of freedom do I have? Well, I get rid of one column and I get rid of one row, and I count it up. I have 4 categories left. So I go back to page 527. And I go to 4 degrees of freedom. And 14.3 is just below 1%, which means reject the null, which means does your married status affect your employment? Yes. The null hypothesis said no, these numbers are independent. We rejected that, so the null hypothesis says yes, there is a highly significant independent or dependence in there. All right, that's it. Okay, I lied. We're not done. There's one more problem, number 7. All right, number 7. The International Rice Research Institute in the Philippines develops new lines of rice which combine high yields with resistance to disease and insects. The technique involves crossing different lines to get a new line which has the most advantageous combination of genes. Detailed genetic modeling is required. One project involved breeding new lines to resist the brown plant hopper. 374 lines were raised with the results shown below. So of all plants resistant, 97 of the lines had that. Mixed results, 184, and all plants susceptible was 93. According to the IRR model, the lines are independent. Each line has a 25% chance to be resistant, a 50% chance to be mixed, and a 25% chance to be susceptible. Are the facts consistent with this model? So I ended up with 97, 184, and 93, and it was supposed to be 25, 50, and 25. Now, if you know your biology, this is Gregor Mendel's Punnett square, right? So if you have a dominant and a recessive gene together crossed with a dominant and a recessive gene, then you should get double dominant 25% of the time and double recessive 25% of the time, and then a mix of dominant and recessive 50% of the time. Okay, but we know that that good old monk was a liar, right? He fudged his numbers. I love how statisticians like to hold that over his head. You know, he's like this amazing scientist, and these little statisticians come in and said, liar! But that's what we do. All right, so 97 plus 184. Wow. I wonder if that happens, if that messes up the videos when that happens. Plus 93. So there are a total of 374. So I need to figure out the expected values over here. So 97 minus 3. Nope, that's not what I wanted to do. 97 divided by, nope. How about I let you guys tell me what I need to do? 0.25 times 374. There we go. And that gives me 93.5, which we're going to round up to 94. Then 184 cut in half is going to be 92. And then 93 divided by 4. Wow, that's not what I wanted to do. Is 23. Okay, so pull up my calculator. Now I'm going to do 97 minus 94 squared divided by 94 plus 184 minus 92. Oh my gosh, that's not right. I'm sorry. 374 divided by 2. That's 187. Okay, so 184 minus 187 squared divided by 187. And the last one's wrong too. 374. You guys are just going right ahead and let me screw this up without telling me. So 94. Plus 93 minus 94 squared divided by 94. Now, what do you think is going to happen here before I push enter? Do these numbers look okay? Yeah, they're off by a little bit. I hit enter and I get a chi-squared of 0.15. And I think I messed up the earlier question we did when we got to degrees of freedom, because I counted the observed and the expected as different categories. So we really only have 3 categories, and when I subtract one of them, I get 2. Now, the answer was right, but I crossed off a column and a row. But really, we only have 1 column. So all we do is cross off a row. So my chi-squared is 0.15, and my degrees of freedom are 2. So I flip back to my chi-squared table. And with 2 degrees of freedom, 0.15 is just about 90%. Is that very likely? Oh yeah, totally. So do we think that the box looks like this? Yes, we do. Yep, we think that these results are accurate. Okay. Now, wait a minute. When we did Gregor Mendel's problem, we ended up with saying he was a liar. Why was that? Do you remember? Well, if you look at the chi-squared graph, which looks like this, we are like right here at 91%. Gregor Mendel was right here at 0.00004%. How likely are you to be that perfect? What did that one question say? Realist, or what did it say? I don't remember. Fantastically unlikely. Yeah, his results were so perfect, they are fantastically unlikely. Okay, we're done for real now.